On the right, if we flatten out the helix, this shows what you have. It's sugar phosphate backbone, which is immaterial because it's all the same no matter where you go. It's a sugar phosphate, sugar phosphate, sugar phosphate, blah, 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 and the whole genome. So that, all that does is sort of keep things in line. Look at India, maybe I'm wrong here, but I think I'm right. If you look at some of the writing in India, Sri Lanka, there's a line, and all of the letters are dangled from that, as if this is a way to keep the letters together. And this backbone is a way to keep these bases in line. Now, the actual order of the bases is what produces each unique gene. This is another picture of the two bad boys and a couple of pictures of the double helix. Now, what is the double helix and what does it do? DNA eventually produces polypeptides, which we'll just loosely call proteins. Chemists are, and the 30 chemists in the class, I apologize immediately. Let's just call them proteins. We have 4 different bases, A, C, T, and G. Adenine, cytosine, thymine, guanine. Now, polypeptide chains have 21 naturally occurring amino acids. Amino acids make up the protein molecule. So how do we go from 4 bases to code for 21 different amino acids of polypeptide chains? Well, let's look at the double helix. If we have one base coding for one amino acid, we get how many amino acids? 4. Let's put 2 together to form some sort of a code. And how many amino acids can we code for then? 16, that's right up there. Right. Well, that's not enough, is it? So it really takes 3 of these bases to code for at least 21. But as a matter of fact, we can code for 64 different things because 4 cubed, 4 times 4 times 4 is 64. It's like 4 squared is 16, 4 times 4 is 16, 4 times 4 times 4 is 64. And that's way over the number that we need, but at least we have enough. So what we have essentially are what we call triplet codons. The codon is 3 different bases, and each base codon, triplet codon, codes for a specific amino acid. And so here we have an RNA. RNA is like DNA, except it's just one strand. RNA, and these are the triplet codons over here. Codon 1, 2, 3, 4, 5, 6, and 7, and this is essentially an RNA strand taken off the DNA. And as your book points out, we have a table of which combinations of triplets produce which amino acids. And so we have all of these producing amino acids depending on the specific combination of triplets. And we also have what we call punctuation. The green one up here is start, and the 3 red ones up there are stop. And it tells the system which produces the proteins where to start your message and where to stop the message. Well, how do we go from DNA to proteins? Well, the DNA molecule is like a non-lending part of the library. You have to go to the reference section, and you have to make a copy from that reference section. And the copy you make is a single strand of ribonucleic acid. And the one that takes it off the DNA, we call the messenger RNA, because it takes the message from the nucleus and takes it out of the nucleus. It sends it to a ribosome, where the work is done. RNA is like DNA, but thymine is replaced by uracil, and is one strand instead of two. The messenger RNA, or mRNA, takes the message to the ribosome structure within the cytoplasm and outside of the nucleus. So the Xerox copy, or it's actually a mirror image of the DNA, is taken out of there. And at the ribosome, the messenger RNA meets the transfer RNA, or tRNA, which consists of three parts. One is the anticodon portion, which matches with the messenger RNA because of obligate bonding. We have obligate bonding. And instead of T, the U will link up with the editor. Second part is the transfer RNA per se, which is a little piece of RNA which codes for what it is supposed to do. And at the other end is an amino acid. And so essentially we get something that just schematically looks like this. You get the anticodon, which is, let's say UCG. Then you get this structure in here, which is tRNA, and that links up with a specific amino acid. Now, this anticodon matches this. So each specific anticodon has a specific amino acid that is attached to it, so that you end up with the appropriate amino acid given the original message from DNA. Is this still okay? I'm going to show another picture here in just a second. Well, what happens with the ribosome is that if we look at the messenger RNA here, the next anticodon will be U, and that will be attached to something, and that will be attached to an amino acid. Then this will be G, C, G, and this will be linked up to another amino acid. And what happens is that these amino acids link up, etc., on down in a very specific order, and the order is made obligate by the DNA. This is one way of looking at it. This is the messenger RNA, the codon. This is the anticodon. This is A, U, UA, GC, etc., etc., etc. This is the transfer RNA molecule, and this is the amino acid it's attached to. And so these then link up. Thymine with valine, valine with glycine, etc., on down. For instance, in the beta chain of hemoglobin, there are 206 amino acids. So if there are 206 amino acids, how many codons are there in the messenger RNA? It's very complex calculus, but let's do it anyway. 206, 3 codons per amino acid. How's that? I think, is that right? Check my math, I'm not good at this.